to one application of integration by parts, which is what this video is about. We're going to show how to derive the integration by parts formula from the product rule for differentiation. One of the applications of it is the Fourier series, and to fully understand the Fourier series you need to understand this integral over here, which I'm just highlighting with a box there, and that integral leads nicely onto this integral, which is the sum of an infinite number of the base trig vectors that Fourier uses to approximate any function. So you can represent any function using infinite sums of sine and cosine functions. That's a basic concept. So integration by parts, how does it work then? Well, you will remember, and if you don't, just look it up, that the product rule for integration is when you have a function that is a multiplication of two distinct functions, each with an x term. For example, as in this case, like sine x cos x. So I'd call the first function u, and I might call that second function v. And you can prove using the same method as for differentiation, I'm not going to do that here, that to differentiate this function, sine x cos x, you'd have to first take cos x and times it by the differential of sine x, and then add that to sine x times by the differential of cos x. And that's a product rule. And you can also see it represented like this depending on the notation being used, but it's exactly the same thing, just different notation. And the key thing being it's for differentiating functions with two functions multiplied together, hence product multiplication. So we're going to rearrange this formula by taking the integrals of both sides, and we'll end up with a formula that looks like the integration by parts formula. And that's where we're heading. So we want a formula that looks like u dv by dx integrated with respect to x is equal to uv minus the integral of the function v times by the differential of u, all integrated with respect to x. That's the final function that we're expecting to, formula that we're expecting to end up with. And that comes from the product rule. So let's start by considering, okay, well remember the product rule is used when you have a function that is actually the product of two functions u and v. So product of two functions u and v. So actually dy by dx, since y is equal to uv, can be written the differential of u times v functions with respect to x. So using that definition of dy by dx, I'm going to integrate both sides, and integrals and differentiation can be used in a similar way to adding and subtracting. So when I'm solving equations, if I have 5x minus 2 equals 10, I can add 2 to both sides because I know that's going to get rid of the minus 2. Well, similarly here, if I have a differential on one side equals a differential on the other, I can integrate both sides and that will still be equal. It's the balance method of solving equations, where you're used to plus and minus undoing each other, times and dividing, roots and powers and logs and 10 to the power of, and now we also have integrate and differentiate as functions within that we can use to solve equations. So that's what I'm doing here. I'm balancing equations effectively, but with a new operation, the integral. So we know the whole point of the integral is that it is the inverse function. It undoes a derivative. So I'm left with uv on this side, and on this side, and on the other side, I've still got v du by dx, and u dv, not du, apologies for that, dv by dx. So as you can see, we're pretty much there now. Look, we're aiming for this formula up here that is the same as you will find in many formula booklets at school level mathematics. And we're pretty much there. We've got the uv over here, and we've got the v du by dx over here. Fantastic, great. So I'm then going to rearrange that one last step. I'll keep the u where it is, and I'll take the v du by dx. So I've subtracted v du by dx from both sides. Let's tidy that up because the notation's not great there, it's a bit confusing. Equals uv minus the integral of v du by dx. So now you can see how the integration by parts has come from the product rule. We started here and we've got to here, which is the same. So how would it be used? Well, when you want to integrate a function, so in this case we substitute in the functions that we want to integrate for u and dv by dx. So when I want to integrate sine x cos x dx, the way I'd use this formula is I'm actually going to label one of them u and the other one the derivative of v, because it would have been, that's the whole point, it would have been before it got differentiated. And obviously I've selected them that way around because it makes it slightly easier, because when I derive sine I'm not going to get any negatives, and when I integrate cos I'm not going to get any negatives either, because that would have been sine x. And so now, because I've treated sine x as u and cos x of dv by dx, and then found their derivatives or integrated them to get these four terms, I now know all the terms I need to substitute into the second part of the formula and hence solve the integral. And the next video will show how to solve this integral. And that's integration by parts.